Hello everyone, my name is Guillermo Baltra and together with John Heidemann, we have titled our work Improving Coverage of Internet Outage Detection in Sparse Blocks. We study outages not only because we can learn about internet infrastructure problems, but also because outages can inform us of the real world. For instance, censorship events like the government-mandated outages in Iraq to prevent student cheating during exams. Through outages, we can track hurricanes on their landfall and also the effects of other natural disasters, as well as the time needed for the network to recover. However, the internet is a large place and outages are rare. Therefore, we need to look everywhere, or at least everywhere we can. Of the 14.5 million blocks in the public unicast IPv4 address space, a large fraction is currently invisible to these outage detection systems. That is, either they don't respond to active systems, or their traffic is not available to passive systems. And the actual size of this fraction depends on coverage overlap of the different available systems. If we look closer to what can be observed, given the signal strength requirements of either passive and active systems, many blocks are unmeasurable. That is, blocks with a very small amount of active users. And then, from the remaining set of trackable blocks, not all blocks produce reliable results. This is because blocks can temporarily drop their number of active users below a system's minimum requirements, and therefore generating false outages. Our contribution is increased coverage. For this, we provide two algorithms, one called full block scanning, or FBS, to recover unreliable blocks to a total of 4 million reliable blocks, and the other, lone address block recovery, or LABR, to improve coverage of unmeasurable blocks. With these two algorithms, we make 96% of all the responsive IPv4 address space trackable. However, there is a small cost, and we do lose some temporal precision to a limited amount of blocks. As I said earlier, our goal is broad coverage for active outage detection systems like Trinocular, for which we propose two algorithms, FBS and LABR. And the system requirements for these two algorithms are: 1. A polyp prober, that is, a prober that limits the amount of probing to infer state, and 2. All track addresses need to be probed before repeating or starting a new probing cycle. And we use 2 calendar quarters of real data to quantify our results. So, why probing politely? Mainly for 2 reasons: to constrain traffic and to track millions of blocks. A polite prober doesn't need to probe all addresses. However, probing politely can fail. For instance, let's say we're tracking 6 addresses for a given block, and our polite probing algorithm constrains to a maximum of 2 probes per round. On the left, we have the true state of the addresses. The arrows are up, and the X's are down. Therefore, we know the block is up since we have 3 addresses up. If we find one is up, we don't need to probe anymore. The block is up. On the next round, if we find the first one down, it doesn't matter. We can probe again to a maximum of 2 per round and find the next address that is up. And this is how polite probing basically works. However, if we reach our limit too early, we can end up with the wrong inference. A false outage. So let's leave our toy example behind and look at the real-world example. This is what a sparse block looks like. In the figure, we have the strip chart of our sample block for a whole quarter. Y-axis are the 256 addresses named after their last octet. The x-axis is time. In green, we have the active addresses. All addresses in this block have responded in the near past. A trinocular run occurs every 11 minutes, where Trinocular sends up to 15 probes to infer state. On the top bar, we see Trinocular state inference. Up, down, and unknown. We can zoom in to see how Trinocular can miss all active addresses in a round, inferring a false outage. In the first quarter of the strip chart, there are only a few active addresses. Trinocular flickers a lot. In the second quarter, we see a lone address, and Trinocular is mostly wrong. As more addresses become active, infer states are mostly right, with a few unknowns, ending with enough active addresses to be always right. Blocks with multiple done events are often sparse. If we look at the cumulative distribution of the fraction of ever active addresses, we find that for 80% of blocks with more than 10 down events, at most 20% of their tracked addresses responded on average, what we call an A value of 0.2 or less, as opposed to 20% of all blocks had at most a value of 0.2. Our solution is the FBS algorithm. The basic idea is force sparse blocks to gather more information before making a decision. We accumulate multiple Trinocular rounds until we complete a full round over all tracked addresses before claiming the block is down. Let's look at an example. Again, we have our truth on the left side. We start probing, and if we reach our maximum without having a full run, it is only a tentative down. So we delay our decision, and we continue probing. If we see an active address, all pending rounds are set to up. Let's say there's a true outage, and address A3 goes down. We keep probing until we complete a full round. Now we can claim the block is down. So how does this look like on the sample block we saw earlier? If we look at the top bar, you can see how FBS fixes all the false outages. Flickering is gone. False outages are fixed. Unknown states corrected. And the last part was good, therefore FBS did not touch. So, thanks to FBS, a previously discarded block as unreliable now is reliable, and we can increase our coverage. The other problem we have to broad coverage is lone addresses. The problem is that a non-reply of a single address is ambiguous. They can be either packet loss hosts going offline, firewalls, empty addresses, and network problems or outages. And outages are much rarer than any of the other options. For this reason, inferring block state from a single address is ambiguous. For example, if we look at the first half of the same street chart we've been analyzing so far, we see on the top bar that FPS detects 4 down events. Then we know that a single address failure can happen, but are usually filtered by other active addresses, and therefore there is no outage. Then we see 3 addresses failing together, which is a strong indication of something going on with the network. Finally, we see that a lone address is driving the block state. However, the down events, as we have seen, are only potential block failures. Our solution is called lone address block recovery, and it is very simple. We accept all up events, but we convert down events to unknown when they're not confirmed by at least 3 different addresses. We know that if, for example, we would like to compute a network's overall reliability, LABR results are biased. That is why we tag LABR marked blocks to allow users of our data to ignore them if they prefer to. So what does this look like in real-world data? 3 or more addresses failing together confirm an outage. However, lone address failures are set to unknown. We can compare FPS results with Trinocular in terms of downtime for a whole quarter. X-axis represents the fraction of time the block was down during the quarter for Trinocular, and the Y-axis represents the fraction of time the block was down with FPS. What we see is, first, 29.5% of blocks are fixed by FPS, that is, they improve their uptime, and 70% of blocks are never affected by FPS, which means these are not sparse. However, there were a few blocks that increased their downtime because Trinocular was marking false up states for these blocks. We can also measure FPS results by the number of events fixed. Trinocular, when compared to a passive system, for which we thank Philippe Richter for comparing our results with proprietary CDN data, the CDN confirmed only 27% of the Trinocular events, with 60% possibly being false. However, this 60% was due to few sparse blocks. Now, when looking at FPS, the percentage of confirmed events increased to 77%. And this is without discarding any block. Furthermore, FPS has 75% more coverage than the CDN and 150 more together with LABR. The small price we pay is a slightly lower temporal precision. The shortest detectable outage duration for sparse blocks is a full run, and sparse blocks only represent 30% of total. And how long the full run lasts depends on the number of ever active addresses and how active they are. Since a block with few active addresses demands more probes per round, decreasing full run duration. So if we look at the cumulative distribution of full run size in terms of Trinocular rounds or time duration, First, let's take as reference 18 rounds, or about 3 hours and 20 minutes, our expected full round upper bound, which will happen if Trinocular sends every round 15 probes to a block with all the 256 addresses being tracked. FBS repairs events shorter than a full round, which are false down events, and accepts events longer than a full round, which are true down event. We see that most events are fixed within 1 round, and therefore no loss. Some 45% take up to 2 hours and 45 minutes, and a very few go beyond our expected upper bound. This is when Trinocular is confident of block state, sending less than 15 probes per round, and thus increasing full round length. And so, our results as promised, with these 2 new algorithms, FBS and LABR, we recover sparse blocks and add more unmeasurable blocks to our list. And as I mentioned earlier, we are able to improve our coverage, making trackable 96% of all the responsive IPv4 address space. So to conclude the presentation, we can increase coverage with a minimal cost. FBS is needed for only 30% of blocks. Most are fixed within 1 Trinocular round and therefore no loss. And almost all are fixed in less than 3 hours. Thank you very much.